Section 11.4, we're looking at what we call in this book the reverse chain rule. I like to call these standard patterns. There are a couple of patterns that we're looking for. This one is one of them. Well, here they are in bold. Look, here's one of them and here's the other one. I'll explain these as we go. But when we have this particular pattern of a function that we're looking for, there's a trick we can use to integrate. Some people like to call it the reverse chain rule as well. Okay. Now, it works like this. In example 8, we've got these integrals, and you might look at those and think, well, that's not too bad. Looks like something we've seen in exercise 11a, b and c, so maybe I can deal with this. Maybe we can shuffle this around, maybe do a bit of clever manipulation of the algebra there, and the same with b. Maybe I can shuffle that around and turn it into something to do with trig that I can integrate. And it turns out, if you try that with certain questions, it's just not going to work. You're just not going to be able to put it into a nice form. Now, if I'm completely honest, I haven't tried with these ones. Maybe there's a clever way of integrating these that's quicker, but they're deliberately rigged up for us to practice this technique on. And this technique works like this. I'm going to take the first one of these, integral of 2x over x squared plus 1. I'm going to imagine that, okay, I can't think of a clever way of integrating it. I can't think of a way of integrating it. But watch this. Natural log of x squared plus 1. What happens when I differentiate that? Well, what I get is 1 over x squared plus 1 times the derivative of the thing in the brackets, which is 2x. Now again, if that's not straightforward to you, then go back and practice chapter 9. It's a chain rule question. We need to do chain rule the quick way. Okay. Now let's have a look at this then. Natural log of x squared plus 1. Oh, there it is, look. When I differentiate that, I get that. So the integral of that must be natural log of x squared plus 1, which is all well and good, but how on earth were you supposed to spot that it's natural log of x squared plus 1? The trick is, if you take the denominator and differentiate it, you get the numerator. So when you've got something which is of the form, function on the bottom, numerator on the top, try natural log of the denominator, differentiate it and see if it works. And you'll find that it will. All right, so there's the thing here. Integral of, we'll ignore the k for the moment, function on the bottom, derivative on the top. Integral of function on the bottom, derivative on the top with respect to x is natural log of the thing on the bottom, f of x, right? So let's just see that again. We've got the integral of cos over 3 plus 2 sine x, and I think, oh, well, if I differentiate the bottom, oh, sorry, that looks a mess, doesn't it? Sine x with respect to x. If I differentiate the bottom, what do I get? Well, the 3 disappears, the sine x becomes 2 cos. Oh, so close, right? The sine x nearly differentiates to cos, but it's not, it's 2 cos. Well, let's try it anyway, right? Let's try differentiate natural log of 3 plus 2 sine x. Well, what we get is 1 over 3 plus 2 sine x times by the derivative of that, which is 2 cos x. Well, hang on a minute. We've seen this sort of situation before. The only thing that's in the way is that 2. So what if I do a half? If I differentiated a half, natural log of 3 plus 2 sine x, then I would get a half of this lot. That 2 on the bottom and that 2 on the top would cancel out, and I'd end up with this thing. So the integral of that is 1/2 natural log of 3 plus 2 sine x. Okay? Now that is why, by the way, if you watched my video on section 11.2, I like to think of it the same way when we have one of those standard integrals with a linear expression in x as the input, because it's the same sort of technique, isn't it? We're guessing the answer, and then we just got to fiddle around and fix the constants that are in front of it afterwards. But as long as we can fix the constants, then we're all good. So there's our technique. So the first thing we're looking for is when you have one function divided by another, just before you do anything else, check, is the top the derivative of the bottom? And when I say is the top the derivative of the bottom, I mean, is it close enough? Is it apart from a constant? If there's a constant flying around, we can fiddle around and fix that one afterwards. The second pattern we're looking for is a particular kind of product of functions, and it goes like this: integral of cos x sine squared x with respect to x. And again, if you mess around and look for it, maybe there's a clever way of doing this, I'm not sure, but in principle, there are some of these where if you mess around for long enough, you still can't do anything with the trigonometry. There's still not a way of integrating it that way, but we can use a special trick, which is this. Try differentiating sine cubed of x. Well, if I differentiate sine cubed of x, what happens? The 3 comes down to the front. 3 sine squared x. Now, times by the derivative of sine, times by cos x, and it worked. Okay, now of course it worked because I'm using a particular trick. What's the trick then? The trick is, and this one is a bit difficult to sort of say, but it's a function to a power times by the derivative of the function. Okay, a function to a power times by the derivative of the function. What does that look like? It looks like this. Again, we'll ignore the k. It's a function to a power times by the derivative of it. Okay, so let's take this example here. We've got x squared plus 5 all to the power of 3. We're integrating with respect to x. That's a function, x squared plus 5 to a power, times by x, which is more or less the derivative of x squared plus 5, isn't it? Okay, it's not exactly, there's a constant, but you know, it's close. So what we're going to do is we're going to try and see what happens if I differentiate x squared plus 5 to one higher power, to the power of 4. Okay, so here I got sine squared, so I tried differentiating sine cubed. In this case, I'm going to get 4 lots of x squared plus 5 to the power of 3 times by the derivative of the thing in the brackets, which is times by 2x. Okay, so that would give me, the 2 and the 4 would multiply together and make an 8. So if this thing differentiates, I get this, which is not quite what we want, but all I've got to do is divide by 8. The derivative of that with an 8th in front of it is this thing with an 8th in front of it, so the 8's cancel out. So the integral of that has to be 1/8 x squared plus 5 to the power of 4. All right? If you look in the chapter, you'll find things like this. There's a function. The derivative of that is 2x, which is nearly x. We've only got a constant that we're going to have to fiddle around with. The derivative of that is e to the 2x, which is there. The derivative of that is an x. Oh dear, what we're going to do? Well, this is x squared plus 4 to the power of minus 3. And the derivative of x squared plus 4 is pretty much x. Okay, it's 2x, but it's close. All right? So this is a function to a power times by the derivative of the function. This is a function to a power times by the derivative of the function. E to the 2x plus 1 to the power of minus 3 times by e to the 2x. Okay? So they get a bit sneaky sometimes, but that's not something we're going to worry about too much. So just since they're here, let's just have a quick look at these. This is a function to a power, 2 plus cot x to the power of minus 3, times by cosec. Well, the derivative of cot is cosec squared. Sorry, times by cosec squared. The derivative of cot is cosec squared. The derivative of 2 is nothing. So the derivative of the thing in the brackets is the cosec squared. It's not the derivative of the bottom is the top. It is a function to a power times by the derivative of the function. So we're going to try 2 plus cot x to 1 bigger than the power. Now the power here is minus 3, so the power we're going to try is minus 2. When we differentiate that, it more or less works. We've just got to shove a half in front. Same sort of thing here. We've got a definite integral, but we're not going to worry about definite integrals because we know about those from last year. But what we've got is sec tan, tan sec to the 4. Well, that is sec to the power of 3 times by the derivative of sec. Sec to the power of 3 times sec tan. Okay? So if I try and differentiate sec to the power of 4, I'll more or less get it. Do you get the picture? How fiddly they are, how kind of sneaky. This doesn't look like a function to a power times its derivative until we write it as sec cubed times sec tan. This doesn't look like a function to a power times its derivative until we write it as 2 plus cot x to the power of minus 3 times by cosec squared. All right, so they're nice tricks, but easy to miss. Good luck with section 11.4.